Okay, thank you. So good morning to everyone. Thank you all for being here, be present on this Thursday session of the fourth LW virtual meeting. I'm Jorge Rueda, the moderator of this session A, Gravity, Astrophysics, and Elementary Particles. So I remember, so I will speaker by speaker of the session morning. You see the program now on the screen. They will be allowed to speak. They become presenter in the GoToMeeting session, and all the other microphones and webcam have to be switched off in the meantime. And please remember, you can type your questions in the chat. I will collect them, and then at the end of each talk, I will ask the question to the speaker. So we have to be very sharp on time. So please be concrete in your questions, and I ask the speakers also to be concrete in their answers. So thanks again, and I think we can start proceed. So first talk is by Nikolay Shakura on the nature of the 35-day cycle in Hercules S1 8 Zilher. So
thank you. Good morning.
Okay, we can see your screen. We can, if you can put it full screen.
Do you see the picture? The first picture, the first slide?
Yes, we see your first slide, but it's not still in full screen.
Thank you. Good morning. And today, I want to tell you about X-ray binary system RZ Hercules X1. Is it okay, the second slide?
Yes.
Hello. The X-ray source, Hercules X1, was discovered in 1971 by the Uhuru satellite. The left picture shows pulsars X-ray radiation with a period of 1.24 seconds. The right picture shows the eclipse of the neutron star X-ray pulsar by the optical star. Below, you see the dependence of the time delay of the X-ray pulse of the orbital phase. One of the components of this system is optical star of about 2 solar masses. Another one is X-ray pulsar of 1.5 solar masses. The pulsar is rotating with a period of 1.24 seconds. Orbital period of this binary system is 1.7 days. Filling of the Roche lobe by the optical star equals unity. The pulsar is surrounded by accretion disk. We observe the precession of accretion disk with the period of 35 days. Here you see the optical light curve depends on the orbital phase. The previous earlier observations of this optical
I think we lost the signal. I think we lost the signal from our speaker. Let's try to restore if possible.
Yes, stop second slide.
Yes. Okay, let's wait a moment. There is apparently connection loss.
We have the main turn on of the X-ray flux. Its duration is about 10 days. Then it disappeared practically at all, and 1 week later appears again, but much weaker, and then again disappeared. All this will be repeated 7 days later. Randomly, the beginning of the main turn-on may occur near the orbital phase 0.2 or near 0.7. We explain this variability by the precession of tilt-warped accretion disk. This picture shows the behavior of different layers of the warp disk depending on the phase of the precession. Here you can see how the projection of the warped tilt disk on the sky sphere change with the phase of the cycle. Observer can see different states of the system Hercules X1 at different phases of the cycle. The reason of random start of at phase 0.2 or at 0.7 is nutation of outer part of the disk. On this picture, you see the passing of HZ Hercules, through shadow created by a tilted warped accretion disk. The arrows show the initial accretion stream velocity. When Lagrangian point is in the shadow, we have the no heating. The stream appears when Lagrangian point comes out of the shadow. The streams flow and of the orbital plane forming the tilt accretion disk. Here I showed the initial stream velocity components of the L1 point in the units of relative orbital velocity. The flows disappeared inside the shadow sector between the outer and inner disk node lines. Here you see the pulse profile, which correspond to different phases of the 35-day precession cycle. This set of pictures demonstrates how the pulse profile evolve. Here you can see how they change with the phase of the precession cycle. It's the main on, the pulse profile in the main on, in the some later in main on, and on this part, we see the pulse profile during the short on. It's very different picture. We explain this evolution of pulse profiles in the frame of the model of free precession of neutron star. What is the free precession of neutron star, or the precession of quasi-spherical body at all? We have the scheme of free precession of neutron star. Omega is the angular velocity of neutron star. I1 and I3 are the inertial moments of the slightly deformed neutron star. 1,3 is the precession axis of neutron star. The period of rotation around this axis is about 35 days. J is the rotation axis of the pulsar. The neutron star rotates around this axis with a period of 1.24 seconds. Phi dot is the angular velocity of rotation around the precession axis. Location of north magnetic pole changes because of the free precession. Observer is in this direction. Here you see the surface of the neutron star and the places where magnetic lines enter into the neutron star. Near the surface of neutron star, the magnetic field has a very complicated picture. We see not only the
Excuse me, Nikolay, we cannot hear you. Hello? Professor Shakura, we cannot hear you.
I will tell about the optical data of this binary X-ray system. Now, let us consider the observational data of the 35-day cycle in optics. This is the data, this is the old data, the time of the observation in last age, and this is the new data. This is our team, and our team continues this observation since the year 2010. The list of participants you can see in the bottom. About 20,000 points of the spectral band B and 13,000 points of the band V were distributed with the 20 orbital phases. This is the 20 orbital phases, and we see as the light curves change during the phase of precession. A special program was created by Dmitry Kolesnikov for calculation of optical light curves of X-ray binaries. This calculation program includes warped and tilted accretion disk and complicated X-ray directional diagram of the neutron stars. We have the certain parameters that was fixed during the phase of 35-day cycle. It's a semi-major axis, mass ratio, Roche lobe, gravity directing coefficient, X-ray reprocessing factor, disk radius, outer disk thickness, the two angles of orientation neutron star, star's polar temperature, binary inclination, and disk maximum opening phase angle phi0. This is on this table we see the parameters changed with the phase of 35-day cycle. X-ray luminosity, the inclination of accretion disk, the fluxes from accretion disks in B and in V, and phase angle of disk. And disk twist. Our disk is warping. Here you see the results of our modeling in B and in V. And here you see the main minimum. Observe it when X-ray source is located behind the optical star, as well as the secondary minimum. And secondary minimum is caused by passing of the accretion disk in front of the optical star in these phases. Here, IZ, the real structure of accretion disk near the magnetosphere is the outer radius of the disk and is the inner radius of the disk. And Z is the angle between nodal lines of the outer and inner edges of the disk. And this you see the results of our modeling. We say that this angle change from negative Z to the positive Z. And we have two positions where and in this position disk is plane. It's plane disk. Here you see the evolution of magnetic dipole vector, and here you see the accretion disk, and you see the magnetic field.
Do we miss Professor Shakura again?
We see the evolution of inner disk with phase of precession. Yes, we can see a solution on this point. On this picture, you hear the evolution of outer edge of accretion disk. It's about 15 degrees on this position, and we observe some declination of accretion disk. It's the result inclination of accretion disk is depend from the dynamical action of streams. In this position, we have strong streams, and inclination is about 15 degrees. And in this position, this inclination is less, is about 10, maybe 7 degrees. Also, X-ray luminosity changes with the phase of 35-day cycle. The maximum X-ray luminosity takes in this position. Maybe you see some dark part of these slides is the X-ray main on, it is X-ray short on, and is the practically X-ray is absent. On this picture, you see the evolution of fluxes from accretion disk with the phase of 35-day cycle. We see the maximum on this phase, the accretion disk. We observe the maximal angle to the observer of accretion disk, and we have the maximum, and we have the minimum, the second maximum, and in B and also in V. On this picture, I demonstrate the phase variability of the angles epsilon out and epsilon in, which are angles between the observer's line of sight and outer and inner radius of accretion disk. We have the we observe the evolution of this angle with phase of the precession. This epsilon is the observer, this epsilon between R in, epsilon in, and R out. There is results of our modeling. And in future, we are going to model main minima. Now we did not model this phase. In order to model orbital phases between 0.0 and 0.1 orbital phases, we will apply the more complex model of the warp disk in the future.
Professor Shakura, you have, sorry for interrupting, 5 minutes left.
I finish. Additional observations should be carved out at the these orbital phases. Such modeling led us to reconstruct the real structure of warp accretion disk. Thank you for the attention.
Thank you very much, Professor Shakura, for your presentation and for being sharp with time. So far, I don't see questions from the participants. So I will ask to ask you one question, if I may. If with the modeling there is any information about the mass of the neutron stars.
Yes. The free precession of neutron star influence on the observations period of pulsar. This period is shorter when the magnetic pole rotates in the same direction as neutron star, and period is more longer, about maybe 10 to the minus 6 to 10 to the minus 6 seconds. But it is difficult to observe. We have some noise in the observation of period of neutron star, but it is real to find this effect, and it was it will be the real confirmation of free precession of neutron star.
Okay, okay, thank you very much. So there is one question from Stanislav Komarov. So how the precession affects the possible observability of the pulsar? Could an eclipse happen? So I repeat the question. How the precession affects the possible observability of the pulsar? Could an eclipse happen?
Eclipse is from the disk. We observe the eclipse when the disk is in.
Hello. Professor Shakura, are you there? I think we missed the audio of Professor Shakura.
Let's still wait a second, maybe he reconnects back. Please,
what about sorry? What about eclipse declination of rotation axis?
Professor Shakura, we missed part of your answer. If you don't mind, please repeat your answer.
The answer to the previous question, because we missed your answer.
I think that how to confirm the free precession of neutron star. It's main problem, and I think that if we will observe the pulsar period, the evolution of pulsar period with
once more, we lost the connection. So I would suggest, Jorge, we can continue, and we can always ask the participant to direct their questions to the speakers by email or other means.
Yes, okay. And then I think I will send a message with the question by email. Okay. So thank you, Professor Shakura, for the presentation. So we move to the next speaker. Next speaker is around. I see him is Eric Howard.
Yeah, that's me. Application, no. Share. Okay. Can everyone see my screen?
Yes, you see your screen, but it's not still full screen. It's not yet. Yes, if you can put the screen.
Is that better?
Yes, a moment. There is a bit delay.
Can you see it?
Not yet. I see black screen.
Okay, I'll stop sharing.
Sorry to interrupt. I guess it's because you sharing the application, not demonstration form. So in PowerPoint, if you share the window, you have to share. Yeah.
Yes. Oh,
yeah.
Okay. Now it
works.
Yes, now it works. So you can start. So I will tell you when 5 minutes will left. Okay.
Oh, that's good. That's good.
So you can start.
Right. So my name is Eric Howard, and I'm a postdoctoral research fellow here at Macquarie University in Sydney, in Australia, at the Centre for Quantum Materials and Applications. working on cosmology and condensed matter systems, specifically cold atoms and designing quantum sensors for dark matter and gravitational wave detection. Today I'm going to talk about phase transitions and condensed matter analogs of defect formation in the early universe, or as it is known, the Kibble-Turek mechanism, scaling mechanism, I should say. So as an outline, I will initially talk about the scaling mechanism, defect formation, and their cosmological context, together with some results we obtained on the scaling out of equilibrium dynamics behavior. And we used matrix product states for it. I'll try also a short conclusion statement about the current findings and future focus on this matter. Here we studied the dynamics of second order phase transitions that may have taken place in the early universe, and analyze the mechanism as well as the formation of the topological defects that emerge from a quench in an analog system in one-dimensional Bose-Hubbard model and the scalar field 5-4 theory. As we all know, in the early universe after the Big Bang, cosmological phase transitions may have been generated by the expansion and the cooling of the universe. During these transitions, the symmetry of the vacuum was broken and new vacuums with space-like separated regions were formed. A challenging problem here in a current cosmology is whether this vacuum contains these topological defects forming during phase transitions. They allegedly occur within 10 to about 35 seconds after the Big Bang in grand unified theories. After a cosmological phase transition at around 1027 Kelvin, the phase of the vacuum would be disordered, possibly giving rise to a number of topological defects. The mechanism behind these processes can be observed in quite a few condensed matter systems today under certain conditions in laboratory. In condensed matter, when a physical system is rapidly driven through a second order phase transition, this kind of vortices or strings, whatever they are created at a density that is dependent on the speed of the underlying transition. The mechanism that we review here would be the combination of two ideas. One was the initial observation of Tom Kibble that made it clear that, at least in cosmological context, these transitions expected to occur in the universe as it was cooling down after the Big Bang, resulting in some form of mosaic of domains of size close to the Hubble radius at the time of the transition. The resulting density of these defects and the other excitations left behind by the phase transitions depend on the interplay of the quench rate, which is the rate that the critical point is traversed, and the critical slowing down, which the system can adjust. And as a result, on the universality class of the transition. The theory would predict a variety of transformations from high to low temperature phase associated with spontaneous symmetry breaking and the evolution of these topological defect structures like domain walls, strings, or monopoles, or vortices, I should say. The model has been applied to different scales from cosmological concepts to atomic systems, such as Higgs field in the very early universe, superconductors, or quantum fluids. Cosmological inflationary theories have grown popular mainly to the lack of such defects within the visible cosmological horizon. So it is important to try to find out if these defects exist or not. We simulated the mechanism using matrix product states, simulations of Bose-Hubbard model, and discussed the non-equilibrium dynamics behavior. So we mainly tried to study the main features of the system state and the behavior after the quench and verify this if this scaling mechanism for zero temperature happens, and employed numerical tools at zero temperature to find the time evolving mechanism behind the defect formation. So in order to explain the mechanism, we start here with the simple figure that shows the exponential divergence of correlation times of a crystallis two-less transition. Left-hand set shows the domain structure of a two-dimensional colloidal monolayer for large cooling rates at the fallout time, and the right inset shows the structure for small cooling rates after some additional coarsening at late times. In the classical case, this process formation would be easy to visualize since the configuration can be seen explicitly. In this case, it would be hard, and that's why simulations are necessary. So we studied this defect from production upon changing a system parameter. So let's assume that when crossing of the phase transition and the final rate, the spontaneous symmetry breaking during a continuous second order phase transition would be controlled by the parameter lambda here. The mechanism will describe the dynamical evolution of this continuous phase transition under the time-dependent change of lambda across the critical value. So the evolution would be characterized by the divergence of a correlation length at equilibrium, which here is psi, as well as the relaxation time at the equilibrium tau of psi, which is a function of the distance to the critical point lambda c. Also would be the time would be dependent on the dynamical critical exponent z as well, and the correlation length critical exponent nu. The constants psi 0 and tau 0 here would depend on the microphysics. They're not very important, while nu and z would depend only on the universality class of the transition. The notions of scale invariance here and universality are central in the study of these continuous phase transitions. Near the critical point, the characteristic length and the time scales diverge, generating collective phenomena which are decoupled from the microscope degrees of freedom, which is quite important because as long as we have a universality class, we can study the cosmological model and the condensed matter model, and it won't matter. Practically, we're dealing exactly with the same transition, and that's the point. The universality class would obey a power law in the quench rate with an exponent given by the combination of these critical exponents of the transition. The same critical exponents will be associated with systems in the same universality class. So it doesn't matter. We're doing this with optical systems as well. In this work, we consider a reduced distance parameter epsilon that depends on lambda and lambda c. And as this epsilon would vary in time, the scaling dynamics will take 3 stages. And if we go back in the figure, we'll see there is a stage of adiabatic, one of nearly frozen, and one on adiabatic again. The system crosses the critical point, and when this happens, the physical phase transition will follow the spontaneous symmetry breaking through a change in dynamics from a high symmetry phase defined by epsilon being negative to a degenerate vacuum manifold for epsilon becoming positive. If the system undergoes a linear quench that would be symmetric around the critical point at time equals 0, the reduced parameter would be dependent on the quench time and would vary linearly in time. So we've got the freeze out time as t hat. Mainly, the formation of these topological defects would be a consequence of the local evolution of the Hamiltonian after crossing a critical point with this delay that we call t hat, and setting up a sort of boundary between the adiabatic and the frozen stage. After the initial adiabatic stage happens, the frozen correlation length would generate these topological defects. So therefore, the adiabacity will be broken. Consequently, I could say that any small change of the control of the thermodynamic parameters will lead to some kind of non-equilibrium behavior. So the critical point would fully control this non-equilibrium behavior of the system, and would define the system trajectory underlying the phase transition in the parameter space. Near the critical point, the equilibrium relaxation time would diverge. So it can be approximated with the time after crossing the critical point, which is tau of t here. And the freeze out behavior would be due to this collective degree of freedom behavior associated with the order parameter that sort of doesn't keep up with any kind of external imposed changes from outside. In other words, the degrees of freedom associated with this broken symmetry will not follow any change of epsilon. Whatever happens, it's not going to change. The average size of these regions would be defined by the equilibrium correlation length epsilon hat right here, following a power law of t hat when the relaxation time scales as follows a power law of epsilon. If d and d capital and small d are the dimensions of the space and of the defects, the density of the topological defects can be calculated for any value of psi in the system. So more specifically, the system would undergo a linear ramp quench in the hopping strength J here across a second order quantum phase transition starting from 0 temperature. I will not go into details. Nevertheless, the Hamiltonian is symmetric around the critical point that we have JC here. And specifically at 0 temperature, the mechanism would predict this, that the scaling of the final density of the defects would be a function of the quench time determined by a single constant that we noted here as K. And that happens if at the critical point, the equilibrium correlation length would diverge with this critical exponent and an energy gap delta E. So in regards to the phi-4 scalar field, the mechanism, as discussed, can be easily specialized to phi-4 scalar field theory in 1+1 dimensions. The system would be defined by an action S and would have a single dimensionless bare coupling G0 and a global Z2 symmetry, which would act from phi to minus phi symmetrically. The theory would exhibit here a second order phase transition in the ground state. And if we define the reduced coupling epsilon here as dependent on G0, then the ground state would be unique, and the symmetry break would depend on the Z2 invariant in the symmetry phase. So to study defect formation in general via Kibble-Theory mechanism in quantum field theory in general, we need to identify all these observables that capture the information about the defects in the system. In particular, to have an observable that allows for a simple estimate of the defect. Yes.
Eric, this is your moderator. Your time is over, so if you can conclude.
Right. Yeah, I was getting very close. So mainly, what I'm trying to say is that these results indicate the consistency of the cosmological picture, that the state of the system follows a symmetry breaking phase transition and is indeed described by the Kibble-Turner mechanism, along with some form of defect ansatz, which we can capture with tensor network techniques that can describe the non-perturbative, non-equilibrium physics of topological defects in the early universe. Thank you.
Okay, thank you, Eric, for your presentation. There is a time for one question, if at all, but I don't see any question right now. So I recall to the participant, if you have any questions of any time, just write in the chat that I collect them for the speakers, and then I'll try to send to the speakers by email. So our next speaker is, okay, we move to Oleg Zaslavskii. Is not yet here. He has to connect. So we move to Stanislav Komarov, if he's ready. Hello, Stanislav.
Ready?
Hello.
Hello.
Okay, Stanislav. Okay, you are there. Can you share your screen with us, please?
Yes. Now.
Okay, we see something, but not yet full screen. If you can put in full screen.
Do you see my presentation?
Yes, we see the presentation, but not full screen.
Yes, now. Now?
Oh, okay, that's right. Okay, so you have 15 minutes. I tell you when 5 minutes are left. Okay, so you can start.
Yes, thank you. My name is Komarov Stanislav, and I will present a work on the reconstruction of relative motion of components of a binary star in gravitational field of supermassive black hole from its redshift. This work was performed with Alexander Gorbatsevich. Let's start with introduction. It is well known that in the center of our galaxy exists supermassive black hole with mass near 1 million solar masses. Also, a large population of stars exist in the vicinity of this supermassive black hole. These stars also called as stars, and one of the more interesting star from these objects is S62 star. Distance for the star to galactic center correspond near 600 geometrical masses. And for example, for star S2, this distance is about 200 geometrical masses. And both these stars are good candidates for testing theories of gravity in the strong field regime. For this purpose, it is possible to observe redshift of light that emitted from the stars and received by observer. Another good possibility is a large population of pulsars that also exist near the center of our galaxy. And these pulsars are also combined in binary systems. For example, in this picture from nature, blue circles represent non-thermal sources that are identified with such binary systems that consist of X-ray pulsars. And the characteristic that is investigated from X-ray pulsars is pulsar timing data, is times of maximum of the intensity of these sources. By investigating this data, it is also possible to determine law of motion of these stars and to test theories of gravity, for example. Our problem is following. As first step, we analyze direct problem is determination of redshift of light from binary star that moves in the vicinity of supermassive black hole. And the next step is the solution of inverse problem. This problem is when we know redshift as function of time of observation, and from this function one can obtain parameters of motion of binary star near the center of galaxy. For this purpose, we use full general theory of relativity. It is well known that equations of motion in general theory of relativity can be obtained from Einstein field equations. The most general case for the gravitational field of supermassive black hole is gravitational field of Kerr black hole. This is more general case for astrophysical scenarios. And we write down well-known equations for time-like and zero geodesics in the Kerr field. Time-like geodesics represent all lines of a star in external gravitational field, and their geodesics represents world line of light that emitted from source and received by observer. And there is well-known methods for solution of this geodesic equation. For the case of Kerr space-time, it is possible to obtain in the form of integrals solutions for geodesics. And these integrals also can be calculated in terms of elliptical functions. In order to solve the problem to find redshift as function of time of observation, it is necessary to solve also boundary value problem for presented differential equations. And apart from this, for example, solution for zero geodesic must intersect both world line of the source and world line of the observer. These points give us boundary conditions for the solution of this problem. And we know solution of equation in terms of elliptical integrals, and due to this, solution of boundary value problem is mathematically equivalent to the solution of usual non-linear equation for certain parameter of light that called impact parameters. And solution of the problem for pulsar can be solved analogously due to times of arrival of pulses of pulsar can be expressed through redshift function by very simple formula. And these problems is follows for the calculation of redshift and for the calculation of pulsar timing data are mathematically analogous. In order to find motion of components of binary, it is necessary to introduce moving reference frame in the vicinity of the center of mass of the binary. The center of mass is moved very near time-like geodesic, but components moves on the another world lines that can be found from these equations. Right, that are write down in Fermi coordinates. The following step is the solution of redshift for the case of binary star. For these purposes, it is convenient to introduce such quantity as Z0 is the redshift for the source in the point of center of mass of binary star. And we write down decomposition of this quantity, whole quantity of redshift.
You have 5 minutes left.
Yes, thank you. If we use such quantity as distance between components of binary ρ and their relative velocity v as small parameters, we use small parameters only v and ρ relative parameters. But, for example, such quantity as velocity of motion of the center of mass can be relativistic or even ultra-relativistic. This parameter is must not be small in our calculations. And time of observations then can be calculated through redshift from the following formula. That is follows from determination of redshift. This is an example for the solution of the problem. And the next step is the solution of inverse problem. Mainly in literature for this purpose, usually you used a direct least square method. His square function must be minimized. His square for z, it consists of two parts. His square for z is the function for measurement of redshift, and part for the measurement of observation positions. But for the observation positions, is usually this quantity has not such precision measurements, and usually for the solution of inverse problem, the part for redshift is used, but minimization of this function is not very simple problem due to z is not analytical functions of parameters of motion. Due to, for example, parameters of light are solutions of nonlinear equation, and this. And due to this, it is possible to minimize this function only numerically. Our approach is based on the another formulas. As first step, we obtain such formula that is follows from the decomposition of redshift, and using this formula, it is possible with certain estimation to perform decomposition of redshift into two parts, on two parts that connect with motion of the center of mass of binary star, and can be solved, for example, from mentioned statistical methods, and part for the relative motion of components. Part of relative motion of components is mathematically very analogous to the motion in usual Newtonian mechanics, and due to this, to solve inverse problem for relative motion, it is possible to use certain well-known methods from astronomy. But due to, if we include in this calculation also components of curvature in external gravitational field, we can obtain more parameters than in usual Newtonian mechanical problem. This is an example of the solution of inverse problem, but our method. Thank you for your attention.
Okay, thank you, Komarov, for the interesting presentation. Let's see if there are questions. I don't see questions so far for you. I have one comment for you. Comment is the following. At the beginning, you say, of course, of your model, you put as the best example the supermassive black hole at the center of the Milky Way. Mm-hmm. But probably you are not aware. We just published our paper in Astronomy and Astrophysics, was published three days ago. Okay, showing the possibility that the center of the galaxy actually could not be a massive black hole, but a concentration of dark matter, exactly explaining the motion of H2 and also the motion of G2. So just to tell you that let's keep open this possibility. That is not. I mean, there is no 100% evidence of the presence of the black hole. So there are still alternatives, and one of these is that there is a condensation of fermions at the center of the galaxy. So I will send to you our paper. So I think that this is it would be very nice if you give also us your opinion about this. Okay.
Yes, I very great thank for your comment and for your papers, if you will send it for me.
Okay, thank you. So we'll move to our next speaker. So I think Oleg Zaslavskii is not yet here. So we should move to Ivan Ohrymenko, who is the next one. So Ivan is ready.
Yes. Hello. Just let me share the screen and. So, can you see it or?
Not yet.
Not yet. Just.
We can see you. You're welcome.
I see some screen sharing is now paused because another window. Try again. Can you see my camera, by the way? Because someone cannot see it.
Yeah, yes, we can see. See your camera.
Right. Yes.
Oh, okay. Now we see your presentation. Okay, so I recall you have 15 minutes. I tell you when.
Just a sec. I want to move the window. All right.
Okay, so if you're ready, you can start.
Okay. So hello, everyone. My name is Ivan Ohrymenko, and I'm a PhD student at Belarusian State University, Department of Radio Physics and Computer Technologies. And my topic is a gravitational wave detector with moving reflectors. So the story of gravitational wave detectors begins with a detector made by Joseph Weber at University of Maryland in 1965. This detector, Weber bar, is a resonant mass antenna, aluminum cylinder in 2 meters long and 1 meter in diameter, which resonates at 1,660 Hertz. In 1986, he claimed he had detected the gravitational wave. However, unfortunately, no other group could repeat the experiment. Thus, there is still a doubt it was real gravitational waves. So it was the first generation of gravitational wave detectors, and the second generation was based on the electromagnetic principle of the detection. It was proposed to use the laser interferometer technique to register the waves. As a result, a well-known LIGO detector was made in 2002. Yet, it was not sensitive enough to detect any gravitational waves. Right after the range of improvements, in September 2015, the first gravitational wave was detected by 2 LIGO detectors, and the Nobel Prize in Physics was given in 2017. Nowadays, 3 gravitational wave observatories operate around the world, and it's LIGO USA, Virgo Italy, and recently in 2020, Kagra, Japanese cryogenic detector, joined them. However, the ground-based detectors covers the small range of the gravitational wave spectrum. In example, a LIGO operates in from 10 Hz to 10 kHz. In order to detect lower frequency, we have to increase the length of the interferometer arms drastically. This can be achieved only in space, where spacecraft equipped with lasers can be positioned at thousands and even millions of kilometers apart. For that reason, there is already an ongoing project of space-based detectors like LISA, and it's
European Space Agency, and Taiji, it's a Chinese detector, and Tianqin. The LISA is going to be placed on heliocentric orbit, and the spacecraft is going to be apart in 2 and 5 million kilometers, and the Taiji is going to be 3 million kilometers arms. The Tianqin is a more simpler version. It's going to use spacecrafts placed around the Earth on high orbit, on high type of orbits. Talking regarding the space, the Republic of Belarus is a space-faring nation since July 2012, when it's launched its own first satellite. We have a Belarusian R&D company in spacecraft engineering, which design and manufacture the spacecraft called Peleng. And moreover, the Belarusian State University launched its first own student satellite named BSUSat-1, and my department was responsible for this, for design and production. So, and it's already signed the creation of a second BSUSat-2. So we have so this gives us some experience in designing and production such satellites. So in the future we can have some collaborations, and it's important to mention that at the time the technical and research tasks are discussed, so we can propose some our topics to be used in such satellite systems. With all being said, I propose a new developed model of a space-based gravitational wave detector based on the system of satellites orbiting a planet. We consider the general case and come up with a system of notation for such detector, and it's S-LIGA NXRZY is a space laser interferometer gravitational wave observatory based on X number of satellites of orbits of Z-type around the planetoid named N. So, and we consider the particular case named S-LIGA E8RG2. So this is a regular shaped system of 8 satellites on 2 orthogonal geostationary orbits of the Earth. 8 satellites divided equally between 2 orbits and placed uniformly so that it forms a 2D shape of square on each orbit. So let's consider these 2 cases at each orbit. So placing in such configuration, each vertex, if each vertex is going to be double source and receiver, so we're going to have 4 owl-shaped classic laser interferometers per each corner of the square. So it means that we can have 8 LIGA detectors in 2 orthogonal planes operating at one time. And we use a geostationary orbit because it gives us a constant connection with the control center on the planet. So we have delivered some equations which can describe this system. And one is an important formula that we can consider the signal between satellites, and we can study the signals between them. So moving next to a 3D case, if we can connect these if you can connect these 2 different orbits, orthogonal orbits, in some special way, so these forms regular forms such as a square cuboid in the first phase and octahedron in the second phase, which means we can we face the problems that such systems are always changing, and but we can distinguish in some short times, we can distinguish some regular forms of these systems. and we consider here the evolution of the 3D form of satellite system from octahedron to cuboid and back, and it's approximately equals to 1/8 orbital period of satellite. This system actually can be placed at any planet of the solar system. So we have calculated the orbit parameters for this detector as LIGO E8RG2 and calculated the key parameters of the interferometer. So you can see in this table, and the most interested cases is going to be the closest planet and the farthest planet. So the closest one is Venus, and it's going to have interferometer arms as 2 million kilometers apart. And we calculated the approximate maximum sensitivity of such detectors. As far as we know, the LIGO, one of the technical tasks of the LIGO, it's a high stabilization of the mirrors and reduce any vibrations in the system. So, but as we know, it could not be stabilized at all, as there are always going to be some vibrations, and even in space, so there are always moving position distortion. And that's why we propose a new type of the gravitational wave detector with moving mirrors. In that case, I developed a special software which simulates such a detector with oscillating mirrors, and which allows us to simulate the work of this detector and to have feeling to provide a numerical experiment and study and analyze the sensitivity of such a detector. So in this software called the LIGO RM, which stands for LIGO Ringing Mirrors. So in this software has a graphical interface. So we can change the configuration of the detector, and it has animation and interactive regime. So we can move our mirrors by just clicking and dragging it. So then we can change the configuration on the detector. We can start the simulation, and we can still affect the ongoing experiment on the fly and immediately see the results of it on the dynamical graphics kind of working detector or oscillograph. So we can choose the.
Left.
Yeah, sorry. Thank you. I'm close. So we can choose the nature of motion of the mirrors, and we have some laws, and we can set up the frequency of such movements, and we can have a numerical data output. So here you can see some generic signals on the LIGO detector with moving mirrors by different laws. So we calculated it, and we can see that different law nature of mirror oscillations would lead to different signals, even without effect on the gravitational wave. And these signals will be designated by the duration variety of the high frequency and low frequency parts of the signal. Also in this software developed, we can burst a gravitational wave and see how it's affect the detector. And we can set up any type of gravitational wave, and to see how it works. So in summary, the new type of gravitational wave detector, laser interferometer with oscillating mirrors, is proposed, and this software simulates such detector with moving mirrors, and is provide numerical experiments and can analyze detector sensitivity, This software supports animation, allowing you to visualize the principles of the LIGO detector with movable mirrors, and it can be used some in educational purposes. The typical signals on the gravitational wave detector with moving reflectors were presented. The model of a new type of space-based gravitational detector in terms of the system of satellites of regular forms orbiting the planet object is proposed. We consider some evolutionary process of such system, and our future research is the class of such satellite systems in order to find an optimal detector configuration and investigate properties of multi-detector systems. So we're going to investigate the general case. Thank you very much.
Okay, thank you, Ivan, for the presentation. I'm checking now the questions, but I don't see questions for you at the moment. Let's see if one question appears. Okay, there is a question from Colin McLaurin. How does the sensitivity compare? What would be a good frequency for the oscillation?
Mm-hmm. Okay, this is a very nice question. So far, we have done modeling or simulating of such signals, and we are going to study the sensitivity. So far, I cannot give you an answer, sorry, because we have not studied the sensitivity, which one would be the best, but it's our target as well, research target.
Okay, thank you. Okay, I think that's no. So we can move to the next. Thank you again, Ivan.
Thank you very much.
So maybe a better name, very good talk, but maybe a better name will be LIGOM.
Oscillation mirrors?
Yes, would be very much more appropriate.
Yes. Actually, I have a previous version. It was like LIGO oscillating mirrors interferometer. Yeah, thank you very much, and thank you. Yes.
Yes, it would be better. Very good work.
Thank you.
Thank you for the suggestion. So let's move to the next speaker. I don't know if one of the previous one show up now. No, I don't see them yet. Okay, so Michael Ivanov.
Yes.
Okay, Michael, can you put it on the screen?
1 minute. For the system of two particles in one composite particle, we can write equation 3. With matrices with algebra shown below. In equation 4, the dimension of these matrices should be 16 times 16. The second equation of the system is equation 10, shown here. Both these equations contain the combination with alpha matrices. If we accept two equations, 11 and 12, we can rewrite our equations as a system of equations 13, 16. The symmetries of this model are considered here for the case of the raw masses of components. In this case, the following sets of components of psi obey the Dirac equations. The sets are shown here. If introduce left and right components of these four component spinors, the components of the view 1/2 of psi k plus or minus psi n, we shall write shortly as k plus or minus n, where plus relate to the right components and minus relate to the left ones. The existence of pair of solutions of equations 13, 14 leads to the SU2 symmetry of the model. The analysis of the equations 15 and 16 shows that namely the ones define the structure of multiplets. These conditions put on the following restrictions. 1. Doublets and singlets of SU2L as well as SU2R cannot exist together. If psi A and psi B are two different solutions, then their components separately may form как убрать ерунду эту? I'm sorry. May form only singlets. The second component of doublets can be formed only from components of one solution. And 4. It is possible to form up to 4 doublets of one of groups SU2L or SU2R. It depends on the variant of the model. Moreover, all doublets are transformed on the interwound group representations, and up to 8 singlets of another SU2. If psi is transformed under the action of generators of SU2L or R, all columns of the matrices Phi1 and Phi1 and Phi2 should be saved, excluding their rearrangements. Let psi A and psi B be solutions of equations 13, 14. The matrices Phi I are such that components of psi A or psi B cannot be the first and the second components of the doublet, because by the SU2 transformations, it would lead to the change of some columns of phi I. It is from psi A single. Only singlets may be constructed. The matrix Phi1 allows a single correspondence beside an identical between components of psi A and psi B. Psi B equal U psi A, where matrix U has the following view. And this correspondence is shown in equation 18. This gives 4 possible doublets of SU2L or SU2R. Moreover, the component placement in column of Phi1 is such that the same transform should be carried out above all four sets of components. If you suggest that one of these possible doublets can be replaced on two singlets, then components of other possible doublets should be all zero or the pairs of singlets of the corresponding U to SU2. The group SU2 is not an only symmetry group of the model. Unlike Phi1, H1 admits 8 types of solutions distinguished by the transposition of psi components. All of them taking into account the transform psi go to V psi are allowed by Phi H2. These 8 solutions are split into subsets of the considered type of psi A and psi B. It tests 4 types of doublets of some psi R or L are admitted. Let us show these possible solutions as the substitutions, skipping solution indices. The second part can be get by the transform psi go to U psi. These solutions are shown in equation 20. Writing them as psi, U1 psi, U2 psi, U3 psi, where UK are the transposition matrices, we have the following algebra for these matrices. Shown below. By 21, all solutions are split into the 2 classes if we identify Psi with UPSI. The ones having only one of 3 properties, being an analog of 3 colors of quarks, it is UK psi, and having all 3 properties, it is psi. So they may interpret in this way the concept of color for the composite system by the additional requirement of the conservation of the norm psi cross psi for every class of solutions. SU3C times SU2 will be the global symmetry group. The chiral properties of solutions are already discussed. The solutions UK psi with k equal 1, 2, 3 form the SU3 triplets, while psi and U psi form its singlets and the doublet of one of SUR or L.
Michael, you have 5 minutes left. Okay.
Yes, I understand. UK psi and UK psi will be the doublets of the last 2. Thank you. I understand. My time is over.
So did you finish, Michael?
Yes, I'm.
So did you finish your presentation now? You have still. Okay.
Yes, I finished.
Okay. Thank you, Michael, for the presentation. So I'm checking now if there are questions for you. Is there any question for Michael? To Michael? No. Okay. I don't see any question. Thank you. Okay. So let's move to the next speaker, Andrej Manko. Okay. Just can you put in full screen, please? Okay, Andrej, you can start when you like. Andrej, we can hear you. Andrej, I think you have still problems with the microphone. We cannot hear you. Andrej. Okay, we have problems with Andrej with his microphone. So I think we have to suspend his presentation for a moment while he fixes his problem with the microphone and move to the next speaker.
Okay, Jorge, let's move to the next speaker.
Let's move to Alexey. He said, yes, I see him around. Then we try to continue to contact with Andrej after. Okay. Alexey.
Do you hear me?
Yes.
My microphone is, well, and my camera, well, I can't turn on my camera. Oh, something on. My microphone is okay, but I can't see. I can't turn on my camera and screen. I put the button, but they don't start. Oh.
Alexey, it's Gregory speaking. May I suggest you, I can show the presentation for you. You will be just asking to change the slide. Would that work? Hello, Alexey? Probably he's
reconnecting, I guess.
Yes, he is configuring the application. Okay, let's see. Well, we still have some time in this session, therefore we can wait for these two speakers. Oh, okay.
Oh, I'm sorry. Do you hear me?
Yes, we can hear you.
Well, but you don't see me. Do you see me?
We don't see you. We don't see your screen.
And do you see my face?
No.
No, you don't see my face. Oh, it's something wrong with the screen and camera. Well,
don't worry, Alexey. You can just make the presentation. I will show your PowerPoint presentation to everyone, so you will be asking to change the slide when necessary. Is that okay?
Okay. I agree with that. With this variant is okay. So my presentation. Okay. Oh yes, everything is okay. Thank you very much. Good morning, dear participants and dear organizers. I am very glad to participate in your conference. My thanks to the organizers for the invitation. And my report is Baryshevsky-Luboshitz effect in spin-polarized electron gas at high temperatures in quantizing magnetic field. Next slide, please. Introduction, next slide. Thank you. Baryshevsky-Luboshitz effect is similar to Faraday effect because it's also, like the Faraday effect, is the rotation of photon polarization plane of light. But here, spin polarized medium, for example, electron gas, is required. And this effect, unlike Faraday effect, is explained by the difference of Compton scattering amplitudes of the same and opposite spin direction on photon and electron, unlike Faraday effect, which is explained by Zeeman effect. Well, this effect, Baryshevsky-Luboshitz effect, was predicted in 1965 and experimentally discovered in 1970s. The example of the book where the effect is discussed, well, you can see. Next slide, please. The problem is the following. If the external magnetic field is small and Landau quantizing can be neglected, then Baryshevsky-Luboshitz effect takes place in the second order perturbation theory on electromagnetic coupling constant. Well, these calculations were made in those books, Baryshevsky, Nuclear Optics of Polarized Media. Well, but in astrophysical conditions, when the external magnetic field is strong, the whole algorithm of calculation changes significantly. Well, because Landau quantizing plays a significant role and it makes a significant influence on wave functions of electrons, then Baryshevsky-Luboshitz effect takes place in the first order perturbation theory on electromagnetic coupling constant. Next slide, please. Thank you. The idea of obtaining the formula for the rotation angle of the plane of linear polarization of photon per unit path in an electron gas at high temperatures in quantizing magnetic field due to this effect was proposed by Baryshevsky and Tikhomirov, Vladimir Grigorьevich Baryshevsky and Viktor Vasilievich Tikhomirov. Well, my chair for, well, my directors of my presentation, my dissertation. It was implemented for cold electron gas at zero temperature approximation in the following papers. Well, the idea belongs to Baryshevsky and Tikhomirov, but the papers were fulfilled well by me. Well, you can see them several years ago. The next slide, please. Well, as far as the approximation of high temperatures is also important and more realistic in many cases, because cold, the degenerate electron gas is a widely spread phenomenon in space, but hot electron gas as well. The new task is to obtain similar formula for non-degenerate or hot electron gas. Well, this is the task of this work. This paper. Problem formulation. Well, next slide. The model of the situation is the following. Let's consider a photon of X range, because the effect, unlike Faraday effect, dominates in visible range. well, and radio range, but this effect, Baryshevsky-Luboshitz effect, dominates in X range. Well, let's consider such a photon passing through hot spin-polarized electron gas in quantizing magnetic field along the vectors of magnetic field strength and spin polarization. Of course, we can choose more general situation when there is some non-zero angle between the wave vector of photon and the vector of spin polarization of magnetic field, but the algorithm of calculation becomes much more complicated in this situation. That's why let's choose this more simple situation. Well, and even in this situation, the calculations are not so easy to do. Next slide, please. Well, the following denotations will be used if a photon passes the distance z along that axis and its plane of linear polarization tends on the angle the phi. The following denotations will be used for this calculation, the phi z. Alpha is electromagnetic coupling constant, Bohr magneton you can see, then Boltzmann constant, absolute temperature, electron number density, Planck constant, magnetic field strength, speed of light in vacuum, electron mass, photon frequency, chemical potential of electron gas, in relativistic, from the relativistic point of view, because it includes rest energy of an electron, then electron momentum along that axis. Well, we don't require electron momentum over other two axes because of Landau quantization. Integrating variable, then some other denotations in order to for more convenient to write the corresponding formulas more conveniently. Well, such as some variables, including the width of virtual Landau level, well, magnetic energy divided by electron rest energy, photon energy divided by photon rest energy, and electron rest energy divided by thermal energy, and some other denotations and special functions. We can see how they are applied on next slides. Next slide, please. Well, some important remarks about all this. The methods of quantum electrodynamics are applied for the angle of rotation calculation per unit path without averaging the result over the moment of electrons. Well, here we use only quantum electrodynamics without averaging. Well, the result depends on pair Z, on the momentum of electron along the z-axis. Well, the example of book you can see. Then, the methods of quantum thermodynamics and statistics are applied for the averaging the result over the momentum. So if we want to make the averaging the result over the momentum of electrons, when use thermodynamics. The example of the book you can see. Well, and only the ground Landau level N0 and S-1, 2 is considered for the contribution to the effect. Why? Because the contributions of all the other levels approximately compensate each other at high temperatures. Well, this level, the ground level, is not compensated, but that's why the calculations become simpler. Next slide, please. Well, and we obtain the approximate formula for this effect at high temperatures. Next slide, please. Well, here are the formula obtained for the calculation of the phi z in electron gas. Well, K1 and K2 in the formula 3 are Bessel functions of the corresponding arguments. Unfortunately, I had no time to fulfill the integration completely, but it seems to me that the result can be expressed by Bessel functions. Well, I will try to do it a little bit later. Well, so you can see that the result depends on the temperature. Well, the exponent depends on the electron number density and so on. And these functions that were on the previous slides are used in Formula 2. Well, the next slide, please. Thank you for your attention. Thank you.
Thank you, Alexey, for your presentation. Now it's some time for questions. Okay, I don't see in the chat any question for you. Okay, I mean, we have one. I have one. So, which is the a specific environment where you expect this this effect to play a role?
This effect can play a role in astrophysics. To estimate some density of plasma, to estimate the density of magnetic fields, and so on, and so on. I don't estimate say that there is the only method to estimate all these values, but this method can be an additional one for the existing the methods that are already exist in astrophysics for those purposes.
Okay, there is a second question from Shueshen. Is it circular polarization produced?
Well, what is the question? How this is polarization produced?
Is circular polarization produced?
Well, circular polarization is can be produced in. There are many astrophysical observations that confirm the existence of circular polarization. Circular polarization is this is not the situation when we consider circular polarization, because this is a situation then when the plane of linear polarization changes the angle of orientation. How this situation appears when we have a linear polarized photon can be expressed as a sum of two photons with right and left circular polarization. But if the amplitude of a scattering amplitude or constant scattering amplitude for right circular photon for the photon with right circular polarization is different from the constant scattering amplitude of a photon with left circular polarization, the summation of these two situations gives us a photon with linear plane of polarization that with constantly changing orientation of the plane of polarization. Is my explanation okay?
Okay, Alexey. So thank you very much for the presentation and for your answers. So
thank you very much.
Okay, so I think I don't see the speaker was missing. Okay.
Jorge, I have an update. There is an answer from Oleg Zaslavskii, and somehow he was not prepared to speak today. We will see if we can manage to insert his talk later on in the program.
Okay, so
because he actually sent the abstract and we received it. But anyway, we can, I think, close the session today.
Okay, so we can close the session. So I would like to thank you all for being here, for attending this session, and so we meet the next session.
Yes, thank you very much, Jorge.
So thank you all, and see you next time, next session. Thank you. Bye-bye.
Thank you so much.